It stands on the plateau like a verdict.
Not merely a monument, but a decision.
Across roughly 2.3 million blocks of limestone and granite. Across perhaps 20 years of labor under the reign of Khufu, with copper chisels that dulled by midday and measuring cords that stretched in the desert heat, one number does not drift. Not once, not meaningfully, not enough to matter. That is the paradox. Because large systems drift. They always do. Empires drift. Measurements drift. Even continents drift. Human effort, multiplied over decades, accumulates error like sand against a wall. And yet here, on the Giza Plateau, something was selected and then enforced. The base of the structure measures on average approximately 230.3 to 230.4 meters per side. North, about 230.253 meters. South, about 230.454. East, about 230.391. West, about 230.357. The difference between the longest and shortest side is less than 20 centimeters across a span of more than 230 meters. That is a variation of under 1/10%. Pause and consider that. Across 13 acres of foundation cut into limestone bedrock, the leveling error is measured in mere centimeters. Not half a meter, not a foot. Centimeters. And then the angles. Each corner strives for 90 degrees and misses by no more than roughly 37 to 45 arc seconds. That is about 1 part in 10,000. In practical terms, the error at the end of a 230-meter side is only a few centimeters. It is not perfect, but it is disciplined. Now lift your eyes to the horizon line. The entire structure is aligned to true north with an error of approximately 3 to 4 arc minutes, about 5/100ths of a degree. It does not point vaguely north. It does not approximate north, but it locks onto it. And not only on one face, all 4 sides obey the same orientation. Then there is the slope, the most consequential decision of all. The faces rise at approximately 51 degrees 50 minutes to 52 degrees. The ancient builders described this not in degrees, but in sect. 5.5 palms of horizontal run for every cubit of vertical rise. 5.5 palms. In modern ratio, that is approximately 14 to 11, a simple fraction. But from that simple fraction, consequences cascade. Fix the slope, and you fix the height relative to the base. Fix the base, and you fix the volume. Fix the volume, and you fix the mass. Fix the mass, and you fix the structural stresses. The entire geometry becomes a network of constraints. And here is where the numbers begin to whisper. Take the original height, about 146.6 meters, multiply it by 2, then multiply by pi. You arrive at approximately 921 meters. The measured perimeter of the base is approximately 921.36 meters. The difference between the calculated circumference of a circle with radius equal to the pyramid's height and the actual perimeter of the pyramid is less than 3/10 of a meter, a deviation of about 0.04%. This is not an argument for mystical encoding. It is something more unsettling. Once the slope was chosen, this relationship became unavoidable. It is an emergent property of constraint. In other words, geometry began enforcing itself, and the builders never violated it. Through layer after layer, course after course, season after season, decade after decade, no creeping steepening, no flattening drift, no cumulative angular slippage. The rule held. Even after the outer casing stones of fine Chura limestone were stripped away over centuries, the underlying core still preserves the intended geometry closely enough for modern surveyors to reconstruct the original slope with extraordinary confidence. Why? Why choose 5.5 palms? Why commit to that ratio? And then refuse to deviate from it across millions of stones? Because maintaining a rule at that scale is harder than discovering one. Discovery is a moment. Discipline is decades, and discipline requires something else entirely, a culture that prioritizes invariance over convenience. Consider what must be controlled for this to occur. Measuring rods must agree with one another across crews. Survey lines must be rechecked. Angles must be recalculated. Errors must be detected before they compound. Someone, or some system, must ensure that today's workers obey yesterday's geometry. If you are finding this journey compelling, if the idea that constraint, not mystery, may be the true lost technology resonates with you, then consider subscribing. Because what we are about to uncover challenges not only how we view the ancient world, but how we understand civilization itself. We often marvel at the mass of the pyramid, but mass is brute force. Constraint is intelligence, and what stands at Giza is not merely heavy, it is consistent. Now let us sharpen the central question. Not, did they know pi? Not, was it symbolic? Not, was it alien? The real question is this: why did it matter that once a geometric rule was chosen, it was never broken? Why enforce angular fidelity to within arc seconds? Why preserve a slope across decades without drift? Why align to true north so precisely that even modern builders struggle to replicate it without instrumentation? This is not the behavior of a culture improvising. It is the behavior of a system stabilizing something. And here is where the tension deepens, because the Great Pyramid does not exist in isolation. Before it, there were experiments. Before it, there were failures. Before it, there were slope changes mid-construction. There was a pyramid that begins steep and then bends. And that bend may tell us exactly why discipline became absolute. What happens when we compare this unbroken rule to what came before? Perfection does not appear without rehearsal. Before the geometry at Giza locked into place, it wavered. Travel back a generation, before the reign of Khufu to the reign of Sneferu, a ruler who seems almost restless in stone. Under him, Egypt experiments. It pushes upward. It tests steepness. It learns visibly in limestone. There is the pyramid at Meidum Pyramid. Today it stands like a ruin of intention. A collapsed core tower surrounded by debris, its outer casing long fallen. Scholars debate whether its failure occurred during construction or shortly after completion. What matters for us is not the exact timing, but the implication. Its slope was steep, approximately 51 to 52 degrees, strikingly similar to the later Great Pyramid. But the internal structural transition from step pyramid to smooth-sided form may not have distributed weight effectively. The casing layers appear to have rested partly on unstable foundations. Something gave way. Stone remembers stress. Then comes the most revealing monument of all, the bent pyramid. It begins confidently, rising at roughly 54 degrees, steeper even than Khufu's later slope. For dozens of meters, the faces ascend at that sharp angle, ambitious, almost defiant. And then it changes. Midway through construction, the builders alter the slope to approximately 43 degrees. The pyramid literally bends. Its lower half and upper half obey different geometric rules. This is not aesthetic variation. This is correction. Something in the internal stress, or foundation stability, or structural calculations signaled danger. The builders responded not by maintaining the rule, but by abandoning it halfway. The bent pyramid is not a failure, it is an admission. It tells us that slope was still negotiable, that angle had not yet become sacred, that geometry could be revised in response to physical reality. Contrast that with what comes next. Under Sneferu as well, the red pyramid rises at a consistent angle of about 43 degrees. It does not bend, it does not adjust. It holds its slope from base to apex. This is stabilization. A lesson learned. The red pyramid proves that a shallower angle distributes weight more safely across the core. It is, in many ways, the first successful true pyramid, geometrically coherent from foundation to summit. But note what is absent. The red pyramid's slope is conservative, approximately 43 degrees, structurally prudent, stable, reproducible. And then, one generation later, Khufu returns to something steeper. Approximately 51 degrees 50 minutes, nearly the same range that once contributed to instability at Meidum. not as aggressive as the initial 54 degrees of the bent pyramid, but significantly steeper than the red pyramid's safe 43. Why? If 43 degrees worked, why not keep it? Here is the divergence. The bent pyramid changes its mind. Khufu's pyramid never does. From the first course laid upon the leveled bedrock of Giza to the final casing stone placed near the summit, the slope remains consistent within minutes of arc. No mid-course correction, no angular retreat, no visible compromise. The rule is chosen and then enforced without deviation. This is new, and it implies something subtle but profound. Between Sneferu's experimentation and Khufu's execution, something matured. Not merely engineering knowledge, but procedural control. Because choosing a steep slope is bold. Maintaining it across 2 decades of construction is discipline. Imagine the organizational implication. Workers rotating seasonally, teams changing, foremen aging, tools wearing down, quarry sources shifting, and yet the angle holds. Not because gravity is forgiving, but because measurement is relentless. If you are beginning to sense that the real story here is not architectural bravado, but systemic stabilization, stay with me. Consider subscribing if you find this line of inquiry compelling, because we are not chasing mystery for spectacle. We are tracing the moment a civilization stopped experimenting and started enforcing. The bent pyramid tells us that early 4th dynasty builders were willing to alter geometry midstream. Khufu's pyramid tells us that by his reign, alteration was no longer acceptable. The rule could not bend, which means the risk calculation changed, the confidence changed, the oversight changed, the tolerance for deviation changed, and perhaps most importantly, the purpose changed. What transformed between Sneferu's adaptive experimentation and Khufu's absolute discipline? Was it improved structural understanding, a refined surveying method, centralized administrative authority strong enough to maintain invariance across decades, or something even deeper, a realization that geometry itself had become a political instrument? Because when a structure never violates its own rule, it communicates more than stability. It communicates control. The bent pyramid bends. Khufu's does not. What changed between experimentation and enforcement? The answer begins at the ground. Not at the apex, not in the hidden chambers, but at the base, carved directly into the limestone plateau of Giza, where geometry first makes contact with the earth. Because before a single block could rise, a decision had to be made. The square must be true. When Sir Flinders Petrie surveyed the Great Pyramid in the 1880s, he measured each surviving casing baseline he could access. More than a century later, engineer Glenn Dash applied statistical regression to reconstruct the original intended baselines from dozens of surviving foundation points. Their conclusions converge. The north side measures approximately 230.253 meters. The south about 230.454 meters. The east roughly 230.391 meters. The west about 230.357 meters. The longest and shortest sides differ by less than 20 centimeters across a span of over 230 meters. That is a variation of under 0.1%. And this is not modern concrete poured with laser leveling. This is quarried limestone blocks set upon bedrock, aligned by sighting instruments and measuring rods. Now widen the lens. The entire foundation, covering roughly 13 acres, deviates from level by no more than approximately 2 centimeters. 2 centimeters across an area larger than many football stadiums. To achieve this, the builders likely cut shallow trenches around the perimeter, perhaps filled with water to establish a level reference plane. Whether by water, rods, or repeated remeasurement, the effect is unmistakable. The base is not approximately flat. It is disciplined into flatness. And then come the corners. Each corner strives for 90 degrees and deviates by only about 37 to 45 arc seconds. That is roughly 1 part in 10,000. In linear terms, an angular error that small translates into only a few centimeters of displacement across the entire length of a side. Pause here. The sides differ in length by up to 20 centimeters, but the angles miss perfect right angles by only a few arc seconds. In other words, the angular precision is about 5 times tighter than the side length precision. This is not accidental. It reveals priority. If the builders had prioritized length above all else, we would expect the sides to match almost perfectly while the angles drift slightly. But the opposite is true. The square is preserved through angle. Length adjusts to protect it. Imagine constructing a vast square, not by stretching a rope and hoping it remains equal on all sides, but by enforcing perpendicularity first, by locking the corners into right angles, and allowing minor length variation rather than sacrificing geometric integrity. That implies angular primacy. Angle governs form. Length obeys. This is a profound shift from what we saw earlier at Bent Pyramid. There, slope changed mid-construction. Geometry adapted. Here at Giza, geometry commands. Even if a side extends a few centimeters longer or shorter than intended, the 90-degree relationship at each corner remains nearly inviolate. The square must be true, the orientation must be true, the slope will depend on that truth. Because once the base square is established with angular discipline, every subsequent layer inherits that constraint. A slight angular drift at ground level would compound upward, distorting edges, twisting faces, misaligning apex. But that does not happen. The edges rise straight, the faces converge, the apex, though now missing, was mathematically inevitable once the base angles were secured. Consider what this required operationally. Surveyors marking out right angles across more than 200 meters without steel theodolites, measuring rods linked end to end, cords stretched, checked, rechecked, perpendicular lines constructed perhaps through isosceles triangle methods or sighting instruments like the Mercat aligning with circumpolar stars. And then, once marked, those lines had to be preserved during excavation of the foundation trench and placement of the first course. If a corner drifted by even a fraction of a degree at the start, the entire geometry would slowly twist. It did not. The implication is chilling in its quiet competence. Before height, there was law. Before mass, there was mandate. The base is not merely a foundation, it is a commandment. Keep the square true. And once that commandment was set, everything else became derivable. If this strikes you as more significant than tales of hidden chambers or speculative symbolism, you are beginning to see the structure differently. Consider staying with this inquiry, because what lies ahead is not mystery layered in myth, but order layered in stone. The question now sharpens: why prioritize angle over length? Why enforce perpendicularity with such ferocity that even minor length deviations were tolerated in its defense? Because angle defines orientation. Angle defines relationship to the Earth's axis. Angle defines whether the structure participates in a larger cosmic frame. Length is local, angle is universal, and if that is true, then perhaps the base was not merely a platform. Perhaps it was a calibration. But calibration for what? If the square at the base was held as commandment, then to what greater reference was it being commanded? Lift your eyes from the limestone to the horizon. The Great Pyramid does not merely sit upon the earth, it addresses it. Its sides are aligned to true north with an error of approximately 3 to 4 arc minutes, roughly 5/100ths of a degree. In practical terms, if you were to extend one of its sides for a mile, it would deviate from perfect cardinality by only a few feet. That is not symbolic north. That is geodetic north. When surveyor Joseph Dorner measured the azimuths in the 20th century, and when later refinements were conducted by researchers such as Glenn Dash, the conclusion remained consistent. The orientation error is extraordinarily small and, perhaps more importantly, systematic. The pyramid is rotated slightly counterclockwise from true north by only a few arc minutes. Now here is where the comparison becomes decisive. The Pyramid of Khafra, rising just southwest of Khufu's, shares a similar slight counterclockwise deviation. And the earlier Red Pyramid also exhibits a small offset in the same general direction. Different sites, different rains, same directional bias. This is not random scatter. It suggests a common alignment method, one that produced a consistent, predictable error, which means the deviation itself is a fingerprint. Now we enter one of the most fascinating debates in archaeoastronomy. In 2000, Kate Spence proposed that the alignment of Old Kingdom pyramids could have been achieved by observing two circumpolar stars, Kochab and Mizar, when they vertically aligned around the pole. Due to axial precession, the relative positions of stars slowly shift over centuries. By back-calculating the alignment errors of different pyramids, Spence argued that one could approximate their construction dates. Her hypothesis is elegant. If the builders aligned their monument to a vertical stellar transit between two stars, then the slight deviation from true north would correspond to the exact year when those stars achieved near-perfect alignment. Precession becomes timestamp. But there is another possibility. In 2016, Glenn Dash conducted an experiment using a simple vertical rod, a gnomon, during the autumnal equinox. By tracking the shadow of the rod throughout the day and marking the arc of the shadow tip, he was able to derive an east-west line of remarkable accuracy. The perpendicular to that line produces north-south. The result? An alignment with a slight counterclockwise deviation, comparable to that observed in the Great Pyramid. The beauty of the equinox method lies in its simplicity. It requires no star catalogue, no advanced astronomy, only patience, clear skies, and disciplined observation. Count approximately 91 days after the summer solstice. Observe the sun's path, mark the shadow arc, bisect it. Geometry emerges from light. Whether stellar or solar, both methods produce something critical: consistency. The same observational protocol, repeated carefully, yields the same systematic bias. And this is the key. The builders were not aiming at symbolic north. They were using a repeatable method to approximate true north with astonishing precision. Even more telling is the ceremonial record known as stretching the cord, depicted in temple reliefs, showing the pharaoh and a priest aligning a structure using sighting tools, possibly the merket, and cords drawn taut between stakes. Orientation was ritualized, but ritual here does not imply mysticism. It implies standardization, because ritual preserves procedure, and procedure preserves accuracy. Consider the implications. To align a structure of this size to within 3 arc minutes requires careful observation over time. It requires selecting a method and adhering to it. It requires rejecting deviations rather than tolerating them. And once the base square was oriented, the entire mass of the pyramid inherited that cosmic alignment. Every stone laid above it would face the same cardinal direction. Every edge would echo the same astronomical decision. The pyramid becomes an axis, not metaphorically, geometrically. But here is what makes this alignment even more revealing. It was not necessary. Structurally, the pyramid would stand just as firmly if it were rotated a few degrees east or west. Gravity does not demand cardinality. Yet the builders insisted on it. They insisted that the monument participate in Earth's rotational frame, that its faces acknowledge the planet's axis, that its geometry be anchored not merely to the ground but to the heavens. And they did this not once, but repeatedly, across reigns, across sites, with slight variations, but the same underlying discipline. If you are beginning to sense that we are not looking at an isolated architectural triumph, but at a civilization calibrating itself against celestial invariance, then you are exactly where this inquiry intends to take you. Stay with it. Because what emerges is not mysticism, but something arguably more profound: systemic reference control. The alignment, however, does not explain everything. True north defines orientation. It does not define steepness, it fixes direction. It does not dictate slope. The face angle of approximately 51 degrees 50 minutes, the sect of 5½ palms, is not a direct consequence of cardinal alignment. One governs horizontal orientation, the other governs vertical ascent. They are independent constraints, and yet both are enforced, which means two different design decisions, one celestial, one geometric, were selected and then preserved without violation. The square at the base obeys the Earth's axis. The faces obey a precise angular ratio. These are separate laws, held simultaneously. And here the puzzle tightens. Alignment explains participation in a cosmic frame. But it does not explain why that particular slope was chosen, nor why, once chosen, it was preserved with the same ferocity as north itself. Because alignment can drift by a few arc minutes without visible consequence. Slope cannot drift without altering height, mass, and structural stress, and yet the slope does not drift either, which suggests that orientation was not the only invariant being protected. There is another constraint, vertical rather than horizontal, that carries equal authority. Alignment ties the pyramid to the Earth. Slope ties it to proportion. And proportion may be where the deeper discipline resides. So we must now ask, if cardinal alignment anchors the monument to the planet's axis, what anchors the angle of its ascent? If cardinal alignment anchors the monument to the planet's axis, what anchors the angle of its ascent? Stand before the Great Pyramid and trace the line of its face from base to sky. It does not climb arbitrarily. It does not approximate a triangle. It rises at approximately 51 degrees and 50 minutes, perhaps a few minutes more, perhaps a few minutes less, depending on which survey you consult, but always within a narrow band between roughly 51 degrees 50 minutes and 52 degrees. That band does not widen as the courses rise. It does not tighten. It does not wander.
The ancient Egyptians did not describe this angle in degrees. They described it in terms of seked, the horizontal run corresponding to a vertical rise of 1 cubit. For the Great Pyramid, the seked is 5½ palms per cubit.
5½. Not 5, not 6. 5½. In their unit system, 1 cubit equals 7 palms. So a second of 5½ palms per cubit means that for every 7 palms of vertical rise, the face retreats 5½ palms horizontally. Translate that into modern ratio, and you arrive at approximately 14 units of rise for every 11 units of run. 14 to 11, a simple rational fraction. And from that fraction emerges the entire silhouette. What matters is not that the ratio exists. What matters is that it is preserved. All 4 faces maintain this intended geometry within remarkably tight tolerance. Even though the fine Tura limestone casing stones that once defined the polished surface were stripped away in medieval times, the remaining core blocks, stepped inward course by course, still encode the intended slope clearly enough that modern measurements reconstruct it with confidence. The geometry survives the loss of its skin. Now compare. The Red Pyramid rises at a far shallower angle, roughly 43 degrees. It is stable, it is consistent, but it is gentler. Its silhouette feels almost subdued when placed beside Khufu's monument. Then consider the Pyramid of Khafre. Its slope is slightly steeper than Khufu's, often estimated around 53 degrees, though its base is marginally smaller. The variation is modest, but noticeable. The discipline remains strong, but the ratio is no longer identical. And as we move forward in time into later Old Kingdom pyramids, we see increasing variability. Slopes shift, precision softens, ratios diverge more freely. The tight enforcement seen at Giza begins to relax, which makes Khufu's pyramid something like a fixed point. It does not experiment mid-construction as the bent pyramid did. It does not retreat to conservatism as the Red Pyramid did. It selects a ratio and then refuses to compromise it. Why 14 to 11? Let us approach cautiously. There is no inscription stating, "We choose this because." No surviving design manual explains the decision. The reasoning must be inferred from consequences. First, structural consequence. A steeper pyramid exerts greater lateral thrust on its internal courses. Increase the angle, and you increase compressive forces toward the center. Decrease it, and you distribute mass outward more gradually. 14 to 11 produces a face steep enough to be visually imposing, yet not so steep as to threaten collapse under its own weight, provided the internal core and relieving chambers are properly designed. In other words, it is near the edge of ambition, but not beyond it. Second, geometric consequence. When the base is fixed, approximately 230.3 meters per side, the slope ratio determines the height. Choose 14 to 11, and the apex rises to approximately 146.6 meters. The height is not an independent variable. It is locked by the slope. Change the slope even slightly, and the height shifts measurably, which means that by preserving 14 to 11, the builders are simultaneously preserving overall scale. The angle becomes the governor of vertical destiny. Third, relational consequence. If one takes the original height, approximately 146.6 meters, and calculates the circumference of a circle whose radius equals that height, one obtains a value strikingly close to the pyramid's perimeter. This relationship is often dramatized, but we must phrase it carefully. It is not that the pyramid contains pi in some mystical sense. It is that when a square base of 230.3 meters is combined with a slope of approximately 51 degrees 50 minutes, expressed as 14 to 11, certain geometric relationships become inevitable. Perimeter divided by height approaches 2 times pi within a fraction of a percent. Not because pi was necessarily encoded intentionally, but because rational slope ratios produce emergent harmonies. Geometry begins to resonate with itself. Now here is the deeper point. Once 14 to 11 is chosen, it propagates constraints everywhere. The internal passage angles must accommodate it. The apex convergence depends upon it. The volume, roughly 2.6 million cubic meters, is fixed by it. The mass, roughly 6 million tons, is implied by it. The work required to quarry, transport, and place stone is dictated by it. All of this cascades from a simple fractional decision, which means altering the slope mid-construction would have been catastrophic, not only structurally, but administratively. Every planned course height, every internal chamber ceiling, every calculated ramp gradient would require revision. The bent pyramid demonstrates what happens when slope changes halfway. Khufu's pyramid demonstrates what happens when slope is sacred. The ratio is selected early, then it becomes law. Imagine the organizational requirement to enforce that law over 2 decades. Each course laid slightly inward relative to the one below. Each layer measured not only in length, but in horizontal retreat. Each deviation corrected before it compounds. You cannot eyeball 14 to 11 across 200 meters. You must measure it repeatedly and reject drift. This is not artistic flourish, it is procedural fidelity. If you are still with me, consider what that implies about the civilization capable of such enforcement. Stay with this investigation, because what appears at first as a simple angle may reveal a deeper architecture of control, not over stone, but over process. The mystery is not that 14 to 11 exists, it is that it does not wander. In complex systems, ratios drift unless continuously corrected. Wood swells, chords stretch. Human estimation varies. Over 20 years, even slight inconsistencies accumulate. Yet here, across 4 immense triangular faces, the slope remains coherent enough that modern surveyors, centuries after the casing stones were removed, can reconstruct it within minutes of arc. This is not accidental persistence, it is active maintenance, which returns us to the central question, why 14 to 11? Was it chosen for structural optimization, for symbolic proportion, for visual dominance against the desert horizon? Or because, once integrated with the square base and cardinal alignment, it produced a geometry that was internally self-consistent, a kind of closed mathematical loop? And if it does form such a loop, What happens when we calculate its consequences precisely rather than rhetorically? Take the measured perimeter of the Great Pyramid's base, approximately 921.36 meters. Take its original height, approximately 146.6 meters. Now divide the perimeter by the height. The result is approximately 6.285. Now take 2 times pi. The result is approximately 6.28318. The difference between the two is roughly 0.028%, less than 0.03%. The numbers are close enough to provoke fascination, close enough to invite speculation, close enough to tempt the imagination toward grand declarations about hidden knowledge. But pause. Resist that temptation, because what matters here is not whether the ancient builders knew pi in some abstract symbolic sense. There is no inscription claiming such intent, no papyrus declaring a cosmic circle squared in stone. What matters is something more structural. The relationship emerges from the seked. If you construct a square base of approximately 230.3 meters per side, and you raise its faces at a slope defined by 5.5 palms per cubit, roughly 14 to 11, you're not free to choose the height independently. The angle dictates the rise. The rise, combined with the base, dictates the perimeter to height ratio. The geometry begins closing in on itself. Let us look carefully at what that means. The seked of 5.5 palms per cubit corresponds to a face angle of roughly 51 degrees and 50 minutes. That angle determines the vertical rise per unit of horizontal retreat. Once the base half length is fixed, about 115.15 meters from center to midpoint of a side, the slope forces the height. Height is not arbitrary, it is implied. And once height is implied, the ratio of the perimeter to that height is also implied. This is not mysticism, it is constraint propagation. The moment the builders selected that seked, they locked in a cascade of geometric consequences. The pyramid becomes a self-consistent system in which each dimension reinforces the others. Change the slope slightly, and the height shifts measurably. Change the height, and the perimeter to height ratio shifts. Alter the base, and the entire balance is disturbed, but they did not alter it. They held the seked. They held the base square. They held the cardinal alignment. And from those held constraints emerges a near circular relationship between height and perimeter. It is tempting to imagine intentional encoding of a circle within a square. But consider the alternative explanation, the more disciplined one. If Egyptian surveyors favored rational fractions, 14 to 11 rather than irrational trigonometric abstractions, and if they enforced those fractions across large scales with high fidelity, then certain harmonic relationships become statistically likely. The convergence toward 2 pi may not represent a symbolic aim. It may represent the inevitable arithmetic shadow cast by a chosen rational slope. In other words, the pyramid does not whisper secrets about transcendental numbers. It demonstrates what happens when a rational rule is preserved across monumental scale. The geometry tightens, relationships emerge, the structure begins to echo itself. This is the deeper revelation. The Great Pyramid is not a collage of dimensions. It is a closed mathematical organism. The base defines the square, the slope defines the triangle. The height emerges from their union. The perimeter reflects the square. The height participates in a circular equivalence. Everything is constrained by everything else. Nothing floats freely. And because the constraints are enforced so rigorously, because the base angles remain within tens of arc seconds, because the slope does not wander by degrees but holds within minutes, the emergent relationships remain stable enough to observe thousands of years later. Had the slope drifted even slightly during construction, the perimeter to height ratio would no longer hover so near 2 pi. Had the base warped more significantly, the internal coherence would weaken. But the system holds, which means the near equality between perimeter divided by height and 2 times pi is not a random fluke imposed on a sloppy structure. It is a byproduct of disciplined geometry. Now ask yourself something more unsettling. Which is more impressive? That a civilization might have approximated pi in stone, or that it selected a rational slope and then enforced it with such unwavering procedural fidelity that emergent geometric harmonies naturally crystallized. The second possibility is, in some sense, more profound, because it implies not isolated brilliance, but sustained control. To preserve 14 to 11 across 20 years of labor means that every course had to be measured against the intended retreat, every deviation corrected before it propagated upward. Supervisors had to ensure that today's stones conform to yesterday's line. This is not inspiration. This is governance. And once the system is tight enough, something remarkable happens. The pyramid ceases to be merely a structure. It becomes a geometric field in which independent measures converge. Height speaks to perimeter, slope speaks to volume, angle speaks to orientation. The monument behaves less like a pile of blocks and more like a solved equation. Yet here is where caution must remain. Convergence does not automatically imply intentional symbolic encoding. Correlation does not automatically imply mystical design. We must ask a harder question. If a rational seced produces near-circular proportionality as a systemic consequence, then how often would such convergence appear in large-scale rational constructions? Is this relationship rare enough to signal deliberate targeting, or common enough to emerge whenever certain simple fractions are enforced across square bases? The answer to that question requires us to step deeper into the mathematics of constraint, because if the convergence is systemic, if it arises naturally from the chosen slope and base dimensions, then the mystery shifts. It is no longer about whether the builders knew pi. It becomes about why they selected a ratio whose enforcement yields such powerful geometric closure. Was the near-circular equivalence discovered and then preserved? Or was it incidental, an elegant shadow cast by practical structural reasoning? If the pyramid is self-consistent because its rules were unwavering, then we are not looking at numerology. We are looking at constraint discipline so tight that geometry begins to resonate. And that raises the central tension to a sharper point. Is this convergence coincidence? Or is it the predictable outcome of a civilization that understood, perhaps intuitively, that once a rule is chosen, its consequences will ripple outward in ways far beyond the original decision? What do you think about this? Share your thoughts in the comments section. Is this convergence coincidence or systemic outcome? Follow the rule backward. Assume nothing mystical. Assume only that one decision was made and then obeyed without compromise. Choose a slope, not approximately, not artistically, precisely, 5.5 palms per cubit, 14 units of rise for every 11 of run. The moment that ratio is fixed, the pyramid is no longer free. Take the base as given, approximately 230 meters per side. That defines half-base distance from center to midpoint, roughly 115 meters. Multiply that horizontal run by the enforced rise ratio, and the height emerges automatically. It is no longer negotiable. The apex is determined before the first upper course is laid. Choose slope and base together, and the height is locked. Now consider what that means operationally. Builders cannot raise the pyramid until it looks right. They cannot decide late in construction to increase height for grandeur. They cannot lower it for convenience. Every course must retreat horizontally by the precise increment dictated by the seced. If one course deviates, the error propagates upward and becomes visible in the apex. So the slope fixes the height. Once height and base are fixed, the volume is fixed. The pyramid's volume is 1/3 base area times height. No artistry remains in that formula. The mass of stone required becomes a consequence, not a choice. Quarrying operations must meet a predetermined magnitude. Logistics must serve geometry. Choose slope and base, and you have chosen how much stone must be moved. Now mass is not merely a number. It distributes stress downward. The internal pressure on lower courses depends on the geometry above. A steeper pyramid concentrates weight differently than a shallow one. A slight alteration in angle alters the center of mass trajectory. With the 14:11 ratio, the load vector travels inward in a predictable way, compressing the core rather than thrusting outward excessively. Thus, fixing the angle fixes how force travels through the structure.
Even the casing stones participate. Their angle must match the intended faceplane precisely, or they introduce micro-instabilities. Remove them millennia later, and the core still reflects the intended geometry because the internal courses were aligned to the same constraint.
Nothing is isolated. Fix orientation next. Align the base to true north within a few arc minutes. Once that is done, the edges inherit azimuths automatically. The northeast edge is no longer merely diagonal. It becomes a line at 45 degrees relative to cardinal axes, adjusted by the minute deviations of alignment. Those azimuths then dictate how sunlight tracks along edges at equinox and solstice. They determine shadow behavior. They determine which edges catch dawn light first. Choose orientation and you fix celestial relationships. This is not symbolism imposed afterward. It is mechanical inevitability. The pyramid is a constraint network. Pull one variable and all others shift. But once set, none can drift independently without visible consequence. Imagine attempting to alter the slope midway through construction. The apex would miss its intended location. The internal chambers already cut into ascending geometry would no longer sit proportionally. Passage angles would misalign. The King's Chamber ceiling beams, placed to relieve stress along predicted load paths, would no longer correspond to actual stress vectors. Geometry enforces obedience. That obedience distinguishes Khufu's pyramid from its immediate predecessor. Consider the bent pyramid at Bent Pyramid. Its lower courses rise at a steep angle, approximately 54 degrees. Midway upward, the slope shifts to roughly 43 degrees. The visual break is unmistakable. The change was not aesthetic, it was corrective. Structural stress likely forced adaptation. The original angle produced internal instability. Cracks and shifts made continuation dangerous. The constraint cascade failed. Once the lower geometry proved too aggressive, the builders altered the rule to preserve the monument. But that alteration fragmented coherence. The upper and lower portions obey different ratios. The height that would have resulted from a single slope was abandoned. The internal distribution of mass changed midstream. The bent pyramid stands as evidence of experimentation under pressure. A decision was revised because reality demanded it. Now return to Khufu. At the Great Pyramid of Giza, there is no visible break in slope, no mid-course correction, no angle shift detectable across its faces. The Seked holds from base to apex. That implies either greater confidence from the beginning or lessons learned from earlier attempts. It implies that once the ratio was chosen, the builders committed to it fully, trusting that its structural implications were stable, and stability is precisely what we observe. The monument stands for over 4.5 millennia, not because of mystical properties, but because its geometric rules distribute force efficiently. The weight of millions of tons of limestone and granite channels downward and inward along predictable planes. Each higher layer is slightly smaller, each retreat governed by the same ratio, creating a compression-dominant structure. The cascade holds. Fix the slope and the height follows. Fix the height and base and volume follows. Fix volume and material logistics follow. Fix material scale and workforce organization follows. Fix orientation and celestial relationships follow. Fix angle and stress distribution follows. The pyramid becomes less an object and more an equation implemented in stone. And in such a system, drift is intolerable. If the base were out of square by significant degrees, the faces would not converge cleanly at the apex. If the leveling across 13 acres were uneven by tens of centimeters, the height would differ across faces. If corner angles were off beyond arc minutes, the ridge lines would twist slightly, producing asymmetry detectable from afar. But measurements show corner precision exceeding side length precision. Angular accuracy dominates linear tolerance. That tells us something subtle yet profound. Orientation and angle were primary constraints. Length could vary by centimeters. Angle could not vary by arc minutes without compromising the entire cascade.
Angle is the anchor.
When angle is sacred in engineering terms, everything that depends on it inherits its precision. That is why the pyramid appears uncannily coherent, not because it hides secrets, but because it tolerates no geometric rebellion. Contrast this with later pyramids, where slopes vary more widely and construction precision diminishes. There, cascades loosen, internal chambers crack, casing collapses, coherence degrades. Without strict enforcement of one governing ratio, the network becomes less tightly coupled. Khufu's pyramid is tightly coupled, and tight coupling produces emergent harmony. Not mystical harmony, but structural inevitability. When every dimension references a small set of rules, patterns reappear across scales, ratios echo in perimeter and height, symmetry echoes in shadows, stress echoes in internal chamber ceilings reinforced by granite beams aligned to predicted vectors. Consider the king's chamber ceiling, massive granite blocks laid flat. Above them, 5 relieving chambers stacked to divert weight. Those chambers follow the same geometric obedience. Their placement is not arbitrary. They sit precisely where the load from the apex would otherwise concentrate excessively. The geometry above dictates the engineering below. Again, cascade. Nothing in the pyramid can drift independently. To change one element is to perturb the entire network. And this is why the Great Pyramid feels different from structures assembled by approximation. It is not merely large, it is constrained. In constrained systems, elegance is not decoration. It is consequence. The second is obeyed, the base is squared, the corners are trued, the orientation is held, the height emerges, the volume emerges, the stress pathways emerge, the near circular proportionality emerges. Each is not separately chosen, each is downstream. This is the ordeal within the stone. The builders did not simply pile blocks upward, they entered a system where deviation would compound. Every day's labor was accountable to a rule chosen perhaps decades earlier. To maintain that obedience across millions of stones requires not only skill, but administrative continuity. Surveyors, overseers, masons, and labor crews had to operate within the same geometric language. Break the language, and the pyramid fractures conceptually, even if it still stands physically. The bent pyramid shows what happens when language shifts mid-sentence. The Great Pyramid shows what happens when the sentence is carried to its grammatical end without interruption. And yet the tension deepens. If the exterior geometry obeys this network so strictly, what of the interior? The ascending passage, the grand gallery, the chambers hidden within the mass, do they reveal the same submission to overarching constraint? Or do they introduce independent variables that disturb the cascade? If the pyramid is truly a closed equation in stone, then its hidden spaces must speak the same language as its faces. What internal geometry reveals the same obedience? If the exterior enforces obedience, then what of the interior? Step through the narrow ascending passage carved deep into the heart of the pyramid. Here, within the living stone, the same discipline persists. Though it is invisible from the desert floor, though no casual observer could sense it. The king's chamber, hewn from massive granite blocks, sits with walls aligned precisely parallel to the cardinal axes, north, south, east, west, each direction mirrored inside, just as it is outside. The sarcophagus within rests not centimeters, but mere millimeters from its intended placement, a testament to repeated measurement and relentless fidelity. The corridors themselves obey the same rules. They twist and rise with intent, maintaining axial discipline through angles that anticipate the structure's vertical and horizontal orientation. Even the narrow shafts, often called ventilation channels, rise at precise inclinations, one roughly 32 degrees, the other approximately 45, subtly echoing the slopes of the faces above. Their alignment is not ornamental. Their purpose may be lost to time, Yet the accuracy of their orientation reflects the same systemic respect for constraints that governs every stone outside. And then there are the hidden relieving chambers above the king's chamber. 5 vast voids, each stacked above the other, carved to prevent crushing weight from overwhelming the chamber below. Though hidden from sight, their edges, their planes, their very placement obey the global orientation. The cosmic alignment enforced on the exterior does not stop at the polished limestone. It penetrates deep into the structure's veins, threading its way through the silent corridors of the pyramid's core. Why carry this discipline into hidden spaces? These chambers are never seen, never ceremonially approached. They bear no inscriptions. They are, by all accounts, secret. And yet, they adhere to the same cardinal axes as the faces above. This is no mere architectural echo. This is intentional replication of a reference frame within the structure. It suggests the builders were not merely constructing a tomb. They were encoding fidelity, ensuring that every part of the system, seen or unseen, obeyed the same immutable rules. Consider the implications. Every massive granite block, every ceiling lintel, every corridor alignment reflects a network of constraints that extend from the surface to the inner heart. The pyramid becomes a holistic system. It is as if the monument itself were a measuring instrument, a reference, a calibration, a fixed point against which other elements could be understood. The exterior is a frame. The interior is a copy of that frame, preserved in stone. Each corridor, each chamber, each concealed void is a continuation of the same language. The discipline inside is as rigorous as outside. No element wanders independently. Misalignment at the core would compromise the cascade, just as deviation at the base would distort the faces. The pyramid's hidden geometry is not decorative, nor ceremonial in a traditional sense. It is referential. It exists to maintain internal consistency, to preserve the integrity of the overall structure. And herein lies the profound twist. Perhaps the Great Pyramid is not symbolic. Perhaps it is not a shrine, a narrative, or an allegory. Perhaps it is a system, a reference point against which mass, angle, alignment, and orientation are continuously enforced. The visible monument may impress the eye, but the invisible discipline commands the mind. If every hidden chamber obeys the same cardinal alignment as the faces above, if even unseen passages maintain angular fidelity, then the pyramid becomes more than a building. It becomes a statement about control, about consistency, about anchoring human effort to a fixed frame that transcends time. The cosmos is acknowledged not through decoration, but through obedience, not through narrative, but through replication. Step back and consider the silent corridors and the empty chambers above the king's chamber. They do not wander, they do not compromise, they do not deviate. Their precision is deliberate, their orientation is enforced, and yet their purpose remains elusive. Perhaps that is the final lesson of the interior. Visibility is irrelevant, symbolism is secondary. The monument speaks in the language of reference, not rhetoric. Its hidden spaces obey rules because the rules themselves are paramount. And if the pyramid is referential on the inside, what does that imply about its function in relation to the world outside? If hidden chambers replicate the external orientation, if every axis is preserved, then the Great Pyramid may not be a monument of tribute, but a monument of measure. A living calibration of mass, geometry, and cosmic alignment. Perhaps what we have long thought of as symbolic ritual is, in fact, rigorous system maintenance. Perhaps the unseen spaces are not empty but active, participating in the structure's obedience to an overarching frame. And perhaps the lesson extends beyond stone, beyond monuments, to the very idea of civilization. That stability, endurance, and universality depend not on what is visible, but on what is faithfully repeated, again and again, even where no eye can see. If the hidden chambers obey, then every line, every plane, every volume of the pyramid is caught in the same invisible discipline. Every hidden space is a testament to constraint. Every corridor a signal of systemic obedience. The Great Pyramid, both outside and inside, becomes less a monument to a person and more a monument to process. And if it is referential rather than symbolic, then the next question comes into focus. If the pyramid measures, calibrates, and enforces its rules, then what does that reveal about the philosophy of its builders? Perhaps it is not belief that sustains such rigor, but understanding. Understanding that control over one variable echoes through the system, and that every rule obeyed reinforces all others. Perhaps the pyramid is not sacred because of who it honors, but because of what it enforces. And if that is true, the next step is inevitable: to explore how every constraint, every ratio, every alignment propagates through the whole structure, creating a network of obedience that extends from the bedrock to the apex, visible and hidden alike. The Great Pyramid may not be a story, it may be a reference. Perhaps the greatest revelation emerges when we return to the corners. Look closely at the base of the Great Pyramid. Here, where the limestone meets the bedrock, every corner is a right angle. But the remarkable fact is not the right angle itself. The remarkable fact is the precision with which it is executed. Surveyors and engineers of the modern era, including Glenn Dash, measured corner deviations down to tens of arcseconds. Average deviations lie between 37 and 45 arcseconds. Across a base more than 230 meters long, that is a staggeringly small error, less than a 50th of a degree. Now compare that to the side lengths themselves. Linear tolerances are generous by comparison, differences of 20 centimeters across more than 200 meters. Corner angular precision is 5 times more exact than linear side measurements. The implication is unmistakable. In the hierarchy of geometric importance, angle was king. It was the first consideration. Side length could accommodate minor variation. Angle could not. This observation reframes everything. The Great Pyramid was not constructed as a sequence of stone placements by eye or by casual measurement. It was surveyed, it was calculated. It obeyed a procedural logic that begins with angular primacy, and that logic is discernible today in the very fabric of the structure. One of the most compelling modern reconstructions of the techniques involved comes from the work of Philippe Clerc, who in 2020 proposed a method known as ATMR, the alignment through measurement of rods. Clerc suggested that the pyramid's corners could have been set using a system of long, precisely cut rods and isosceles survey triangles. By measuring the angles between rods of fixed lengths, builders could predict where each corner should fall with remarkable accuracy. Clerc's calculations predicted a deviation of approximately 35.6 arcseconds. The observed measurements, 37 to 45 arcseconds, align almost perfectly with the prediction. This is not coincidence. This is a fingerprint of method. It is evidence of procedural precision, not mystical inspiration. Consider the practical implications. Achieving tens of arcseconds accuracy across hundreds of meters requires a disciplined process. It cannot rely on chance, nor on improvisation. Every stake, every cord, every rod must be positioned carefully. Every measurement must be repeated and verified. Every angular discrepancy, however slight, must be corrected immediately. In other words, the process itself enforces fidelity. And it is here that the pyramid begins to tell a story not only of stone, but of society. Because such precision is not the product of a single genius, nor of a small team working in isolation. It is the product of sustained, coordinated effort over decades. Surveyors must be trained, craftsmen must adhere to instructions, supervisors must enforce standards. Workforces must synchronize their labor with the measurement system, ensuring that errors do not accumulate. This leads to an unsettling yet fascinating conclusion. The Great Pyramid reflects a civilization organized around process control, not just labor control, not just monumental ambition, but a culture capable of sustaining methodological consistency across generations. One team may begin the lower courses, another, decades later, continues the upper reaches, and yet the corners remain true. The faces remain aligned, The slope remains fixed. The system transcends individual actors. Contrast this with the bent pyramid, where slope changes mid-construction. There, procedural oversight was either insufficient or intentionally modified, and the geometric network could not maintain itself. The result is a pyramid with two distinct angles, a visible split in the structural narrative. At Giza, the discipline is unbroken. The constraint network propagates from base to apex, exterior to interior, and through hidden chambers. And yet, consider the sophistication required just to begin. Measuring angles with rods over tens of meters requires knowledge of proportional scaling. It requires understanding that long rods, cut straight, preserve angles better than stretched cords. It requires a grasp of isosceles triangulation repeated across space. It requires anticipation of material variation. Limestone expands in heat, wood can warp, cords can stretch. Error must be anticipated, and corrections must be systemic. The precision at the corners, then, is not an isolated technical achievement. It is an expression of cultural capacity. It is a signal that this society understood the cascading consequences of a small angular deviation. One corner off by even half a degree would ripple through the entire constraint network. Slope becomes inaccurate. Apex shifts, stress vectors misalign, internal chambers risk structural compromise. Such understanding implies education, standardization, and communication. Workers were not simply following orders. They were executing a shared language of geometry, a procedural literacy that must have been embedded across generations. Records, training methods, and supervisory protocols now lost were evidently sufficient to maintain the fidelity of execution. And this is why the corners speak louder than the stones themselves. They reveal the intellectual architecture behind the physical architecture. The Great Pyramid was not merely lifted by manpower. It was guided by thought, by foresight, by the discipline to measure and enforce consistency. Its precision is procedural, systemic, and cultural. Step back further. The corners set the stage for everything else. Once angular primacy is enforced, slope ratios follow, orientation holds, height emerges, internal chambers align. The corners are the nodes of a geometric network whose influence cascades through the entire structure. No element can drift independently. Each course, each block, each hidden chamber owes its placement to the accuracy of those original angles. Now consider the scale of this orchestration. 2.5 million blocks, tens of thousands of workers over decades working in the open desert without modern instruments. Yet the corners remain truer than many modern constructions. The society capable of sustaining that must have had exceptional organizational discipline, meticulous record-keeping, and intergenerational continuity. It is not simply engineering, it is civic engineering. A civilization oriented around stability, measurement, and obedience to constraint. And so the Great Pyramid offers a revelation. Its corners are not merely endpoints of stone. They are the first evidence of a civilization in which angular measurement, geometric discipline, is the foundation of societal coherence. We can call it the angular first civilization. One that understood that if you could enforce fidelity in geometry, you could enforce predictability in construction, logistics, and ultimately culture. And yet the deeper question remains: what kind of society not only invents such methods, but sustains them across decades? One that can preserve intent beyond individual lifetimes, that can teach, supervise, and maintain a network of obedience. One that recognizes that procedural precision is as vital to monumental endurance as the stones themselves. If the corners reveal procedural discipline, then the question becomes urgent. What social, administrative, and cultural systems allowed a civilization to prioritize process above expedience, to value the fidelity of method as much as the outcome of grandeur? The answer may lie as much in the human network as in the geometry it produced. And if the society can enforce angular obedience to such an extraordinary degree, what else could it enforce? What other rules, invisible to us, governed daily life, labor, and knowledge? If geometry could be preserved for millennia, perhaps other systems of measurement, calendar, or ritual were enforced with equal rigor. The corners are more than stone. They are evidence. They are a window into a civilization that understood constraint as the ultimate tool of control. And as we step back from them, the next question arises inevitably. How does that discipline manifest in the pyramid's other geometric choices? Its proportions, its orientation, and ultimately its purpose? What kind of society sustains that? What do you believe about this? The corners speak, the faces speak, the hidden chambers speak, and yet one question still hovers above the desert. How is it possible to sustain such obedience over decades? To hold every face, every angle, every internal passage under the same disciplined rule while the seasons change, while thousands of workers rotate in and out, while the sands of the Giza plateau shift slowly beneath the stone. The construction of the Great Pyramid was not a project of months or years. Scholars estimate it required somewhere between 20 and 27 years, an entire generation of labor. And during all that time, the pyramid held its chosen slope, its square base, its cardinal alignment. Nothing drifted, nothing warped, nothing reset. Imagine for a moment the scale of human coordination. Thousands of men moved stones of multiple tons across the plateau. Some quarried limestone at Tura, some brought granite from Aswan, some carved blocks and polished surfaces. Crews rotated with seasons and conscription cycles, yet each new team had to pick up exactly where the last one left off. Each stone had to conform to the geometric language set by those who started decades earlier. A single misaligned block could ripple outward, breaking the cascade of constraints. And yet, no misalignment threatens the apex. The discipline endured. This is not merely manpower. It is procedural fidelity. Standardization must have been central. The Egyptian cubit, the basic unit of measurement, was not simply an approximation of a human forearm. It was a standardized length, repeatedly verified, likely reinforced with rods and plumb lines, calibrated across the site. Without such uniformity, the strict enforcement of slope, angle, and alignment would have been impossible. One team measuring slightly differently than another would introduce cumulative error, yet no such error is observed at the scale of the pyramid. Error correction must have been continuous, systemic, and rigorous. Surveyors and overseers could not wait for problems to accumulate. Every course had to be measured repeatedly, every corner checked, every face examined. Deviations of mere centimeters had to be corrected before the next layer compounded them. Each crew had to internalize not only the rules, but the means of verification, ensuring fidelity without constant instruction. This is a culture in which process is as important as outcome, in which obedience to constraint becomes a societal principle rather than an ad hoc decision. Supervision continuity is another key element. Projects of this magnitude require leadership that outlasts seasons and lifetimes. The Great Pyramid could not have been the work of a single foreman or even a single generation of architects. The oversight required to maintain slope, alignment, and base precision had to be institutionalized. Responsibilities passed from one generation to the next, from one overseer to the next, without the discipline weakening. Knowledge could not have been oral alone. Procedures, measurements, and corrections must have been codified in some form, perhaps through logs, rods, reference stones, or ritualized practices, sufficient to preserve intent for decades. It is here that the human aspect becomes extraordinary. Imagine walking the site in the early morning, a surveyor checking the shadow of a gnomon against a cord stretched across a squared-off corner. Every day, every season, the same measurements repeated, every error logged, every correction enforced. Laborers hauling massive blocks had to trust that these invisible rules were accurate because deviation was not tolerated. The culture itself had to internalize precision, instill accountability, and propagate knowledge continuously across time and labor rotations. And consider the scale of cognitive discipline. Workers were not simply placing stones. They were participating in a system that encoded measurement, geometry, and orientation across millions of blocks. The pyramid was not a static blueprint to follow blindly. It was a living network of constraints that required awareness, observation, and verification. The discipline was as much intellectual as physical. Contrast this with what followed in later generations. After Khufu, pyramid construction continued, but the exceptional rigidity of constraint began to loosen. At Giza, the pyramids of Khafra and Menkaure demonstrate impressive workmanship, yet subtle variations begin to emerge. Slopes shift slightly, corners relax. Precision in alignment becomes less absolute. It is as if the culture of enforced fidelity, the procedural rigor that defined Khufu's era, started to weaken. Perhaps the political centralization required to maintain that level of control could not be sustained. Perhaps administrative priorities shifted. Perhaps knowledge transmission was less exact, or labor organization less disciplined. The lesson is clear. The Great Pyramid is not just a monument of size, but a monument of culture. Its endurance is as much the product of societal structure as it is of engineering. The stone obeys because the people obeyed. The constraints persisted because the culture prioritized fidelity to process above all else. It is a rare intersection of mathematics, labor, governance, and cultural continuity. And within this continuity lies the extraordinary paradox. A civilization capable of preserving a single slope, a single set of angles, a single alignment over decades could, theoretically, repeat this achievement indefinitely. Yet it did not. The discipline was intense but fragile. It required extraordinary organization and belief in the fidelity of the system. Once the societal conditions changed, the constraints loosened. Later constructions reflect this. They are impressive, but the self-consistent network that underpinned Khufu's pyramid begins to fragment. To maintain slope over 20 years, to enforce base leveling over 13 acres, to ensure alignment within a few arc minutes, these are not trivial tasks. They require shared knowledge, shared purpose, and rigorous enforcement. Standardized units, repeated measurement, careful oversight. These were not optional. They were existential to the structure. Each course of stone was a test of discipline, each deviation a potential catastrophe, and yet the Great Pyramid survives today, a testament to the efficacy of that culture of constraint. In some ways, the monument becomes a mirror of its builders. The fidelity of stone reflects the fidelity of society. The rigidity of angle mirrors the discipline of administration. The consistency of slope mirrors the continuity of knowledge and the precision of leadership. The pyramid is not merely architecture, it is civilization rendered in geometric form. And so the question becomes unavoidable. If the culture required to maintain such discipline over decades could produce a monument that endures for millennia, what happens when that culture changes? What happens when oversight falters, when standardization relaxes, when procedural fidelity erodes? The next pyramids, built after Khufu, hint at the answer. Subtle changes emerge in slope, in alignment, in internal precision. The network of constraint begins to fragment. The miracle of coherence is harder to sustain. Yet even as later pyramids show signs of weakening fidelity, the question remains profound. How did a society operating without modern instruments sustain the precision necessary to maintain slope, base, and alignment simultaneously for decades? What administrative, social, and technical mechanisms made this possible? And perhaps most importantly, what lessons can we draw from a civilization capable of preserving such disciplined control over both time and scale, only to see it diminish when the human systems that enforce it change? The Great Pyramid stands, immutable, its edges, its slope, its apex, each a witness to the discipline of the people who built it. And as we prepare to move beyond Khufu's reign, we are left to ask, when that level of constraint fades, what remains? How does the discipline of a civilization persist or fail once the human machinery that enforces it is no longer absolute? What happens after Khufu? After Khufu, the story of pyramid construction takes a subtle but telling turn. The monuments that followed still soar against the desert sky, still impress the eye, still speak of power and ambition, yet the language of precision begins to falter. The once sacred discipline that governed every angle, every slope, every alignment does not vanish overnight, but it softens. Casing stones lose their immaculate fit. Tiny gaps appear between blocks that would have once been impossible. Cardinal alignment drifts ever so slightly. The edges no longer point true with the same unwavering fidelity. Structural degradation becomes visible in ways previously unimaginable. Some later pyramids reveal cracked cores, collapsed outer stones, uneven courses. The rigor that once protected Khufu's apex for millennia begins to erode. The cascade of constraints, so carefully managed for decades during Khufu's reign, becomes looser, more susceptible to error and natural forces. Part of this shift reflects human factors. The reigns of pharaohs after Khufu are shorter. Administrative continuity is fractured. The concentration of authority, the centralized ability to maintain procedural enforcement across tens of thousands of workers, begins to weaken. Without decades-long stability at the top, the discipline that preserves geometry falters. Where Khufu's project was uninterrupted by political turmoil or succession disputes, later pyramids are subject to the vicissitudes of time and governance. The geometry relaxes, slopes are less consistent, seched ratios shift ever so slightly, corner angles wobble in comparison to their predecessor, linear tolerances drift. The internal chambers, while still remarkable, no longer mirror the perfection of Khufu's pyramid in absolute fidelity. The cascading obedience of the constraint network weakens. And here lies a profound lesson, the sacred rule of geometry. The idea that a chosen slope or angle must never vary was historically bounded. It was not an eternal law imposed on stone, but a law maintained by a civilization capable of extraordinary organizational coherence. Once the social mechanisms that enforced it weaken, even the mightiest stone monuments begin to show evidence of human imperfection. Was the constraint discipline tied to centralized stability? The evidence suggests it was. When power, labor organization, and procedural oversight are concentrated, geometric fidelity is preserved. When decentralization, political uncertainty, or administrative turnover occurs, the discipline softens. The stone obeys only as faithfully as the people who shape it. The Great Pyramid survives because the culture that built it could enforce its rules across decades, across generations, across a workforce of thousands. Later pyramids reveal that once the societal glue loosens, the cascade of obedience dissipates. Geometry is no longer sacred, it becomes negotiable, approximate, even aspirational. And yet the lesson remains etched in the surviving monuments. Precision is not merely a technical achievement. It is a reflection of governance, of culture, of the capacity of a civilization to sustain order in both labor and thought. If fidelity requires centralized stability, then the erosion of that stability explains the gradual decline in pyramid discipline. The question now becomes inescapable. Was it power alone that allowed such consistency, or was there a deeper societal understanding of constraint that extended beyond mere hierarchy? Perhaps the greatest revelation of all is not to be found in hidden chambers, nor in mystical measurements, nor in lost knowledge. It is to be found in the very consistency that so frustrated and fascinated scholars for centuries. Step back from the desert, from the dust and sand, and observe the Great Pyramid in its entirety. Across millions of stones, across decades of labor, across generations of rulers, one thing stands unshakable: its geometry. And it is here that the narrative shifts, from one of construction to one of purpose, from one of monument to one of reference. The pyramid is not a repository of secrets. It does not hide cryptic messages or encoded knowledge for the initiated. It does not require symbolic interpretation to impress the mind. Its mystery lies elsewhere, in the discipline of its construction, in the inviolability of its rules, in the unbroken fidelity of its form. Every line, every plane, every axis is deliberate, repeated, and maintained with precision that modern surveying marvels at even today. This is a monument defined not by decoration, but by stability. Consider what is stable. Lengths of base sides measured to the nearest centimeter adhere to a tight tolerance over 230 meters. Corner angles, the very foundation of geometric coherence, are maintained to tens of arc seconds. Orientation to true north persists within mere arc minutes. Face slopes, once chosen, are never violated. Even ratios such as the seked, rise to run, remain consistent across all four faces. This is not chance, it is enforcement. It is adherence to an immutable framework. And when one observes the internal spaces, the hidden corridors, the relieving chambers above the king's chamber, the same story emerges. Axes parallel cardinal directions. Shafts rise at precisely calculated angles. Even the sarcophagus fits with millimetric accuracy. The internal geometry mirrors the external. The invisible obeys the visible. The interior reflects the exterior. The monument is self-consistent at every scale. This is the signature of a reference frame. A reference frame is not about storytelling. It is about stability. It is about providing a fixed point in a world where everything else shifts and drifts. When measurements are taken relative to a reference, one can be confident in their consistency. When a network of constraints is implemented across both external and internal geometry, the object becomes a benchmark. The Great Pyramid is, in essence, a physical baseline, a calibration device in stone. Its lines, its slopes, its corners, all enforce relationships that remain invariant. By stabilizing these quantities, the pyramid provides a framework against which other measurements, other constructions, and perhaps even other observations can be anchored. It is geometry as standard, precision as principle, stone as instrument. The monument transcends narrative or ritual. It exists as a point of comparison, as a constant against which other variables may be measured or controlled. In practical terms, the implications are extraordinary. A stable slope and fixed base define an apex that is guaranteed. Fixed orientation allows celestial observation to be referenced to a known geometric frame. Corner angles define precise axes along which subsequent constructions can align. Ratios encoded in the slope, the seked, and proportional relationships ensure that internal passages, chambers, and structural stresses maintain systemic coherence. Any deviation would disrupt the calibration. The builders could rely on the consistency of their work to plan, predict, and maintain the structure across decades. Viewed in this light, the monument becomes more than the sum of its stones. It becomes a system of reference, a measure against which both natural and human scales can be evaluated. It is not symbolic, it is operational. The pyramid does not whisper secrets. It enforces standards. It guarantees that certain measurements, certain alignments, certain relationships will remain stable over time. In doing so, it allows everything else to be judged, adjusted, or calibrated against that unwavering frame. And the lesson is not only architectural but philosophical. Human societies, like the stones themselves, are subject to drift. Traditions, laws, and institutions waver. Political systems rise and fall. Knowledge becomes corrupted or lost. Yet within the pyramid, drift is impossible. Within its design, the creators imposed a rigid system, one that persists for millennia without decay. It is a statement about permanence, about the value of fixed reference, about the power of consistency in a mutable world. Even when we look at the surrounding plateau, the secondary pyramids, the causeways, the temples, the entire Giza complex, one senses the shadow of this principle. Though the secondary structures do not achieve Khufu's perfection, they are laid out relative to it. The Great Pyramid becomes the standard, the baseline. All else orbits around its fixed geometry. Its corners, faces, and slopes dictate orientation and alignment for structures that follow. It is both literal and conceptual gravity. Everything is measured against it. And yet, the question deepens. If the pyramid serves as a reference frame, what is being measured? What is being stabilized against this fixed baseline? Is it the horizon, the stars, the sun's path across the sky? Perhaps. The precise orientation suggests awareness of celestial relationships, hints at early astronomical observation, and demonstrates the capacity to anchor earthly constructions to cosmic patterns. Perhaps it is the behavior of the stones themselves, their alignment, stress, and stability, ensuring that the construction techniques achieve reproducible results across decades and generations. Or perhaps the calibration extends beyond physical measurement. Perhaps it is a societal calibration, an implicit encoding of process, order, and fidelity. By demanding that labor, measurement, and oversight adhere to rigid constraints, the pyramid trains a civilization to respect precision and continuity. The structure becomes both literal and metaphorical standard, an object lesson in the consequences of constraint, the benefits of obedience to rules, and the durability of systemic discipline. The more one contemplates it, the more the Great Pyramid's purpose transcends conventional categories. It is not monument, nor tomb, nor temple alone. It is a reference, a fixed point in both space and thought. Its geometry does not yield, it cannot bend to desire or whim. It is the embodiment of invariance, a stone anchor in a shifting world, a device that calibrates both physical measurements and perhaps human understanding itself. If this is true, then the implications ripple outward. Every axis, every slope, every hidden passage, every corner, each becomes a datum, a point from which other things may be measured, aligned, and evaluated. It is a network of constraints with enduring consequences. The pyramid is not a repository of mystical knowledge, but a monument to measurement discipline. It is not a puzzle to be solved, but a standard to be respected. Its power lies not in secrecy, but in fidelity. And yet the ultimate question looms. If the pyramid is indeed a calibration object, what exactly was being calibrated? Was it the earth, the sky, human labor, societal order, or some combination of all three? Was it intended as a tool for observation, a template for construction, a means of maintaining cosmic awareness, or a subtle codification of process? The geometry is clear, the discipline is evident, but the purpose, the target of its calibration, remains one of the most profound mysteries left to consider. If every stone, every angle, every internal chamber is aligned and constrained as part of a reference system, then the Great Pyramid becomes more than architecture. It becomes a lens through which the ancient builders engaged with the world around them, stabilizing one constant so that all else might be measured. And that constant, preserved for millennia, whispers a question we are only beginning to understand. If we too desire permanence and understanding, what are the baselines we choose to stabilize? If true, the next step is unavoidable, to explore what the pyramid's calibrated geometry might reveal about its relationship to the cosmos, to the desert, and to the civilization that built it. What then was being calibrated? What are your thoughts about this? Perhaps the most profound lesson of the Great Pyramid lies not in its stones, nor even in its geometry, but in the principle those stones embody. Step back from the apex, from the desert sands, and consider the idea that underlies its construction, that civilization itself cannot endure without stable measurements, without reference points that remain constant across time, space, and generations. The pyramid is more than stone. It is a monument to the philosophy of constraint. It is a testament to the understanding that when baselines drift, society falters. Look closely. In a civilization without invariant reference points, small errors compound. Taxation, for example, relies on measured land, accurate counts, and predictable yields. If the length of a cubit is not consistent, If the orientation of a survey line shifts, the entire fiscal system becomes imprecise. Collections are unfair, disputes erupt, and trust erodes. Similarly, architecture relies on precise measurement to ensure stability. A deviation in foundation alignment or slope may be small at first, yet it cascades through the structure, creating stress, cracks, or eventual collapse. Without fixed measures, buildings cannot endure, neither can societies that depend on them. Timekeeping, too, is vulnerable. Calendars require observation of the sun, the stars, and the passage of seasons. Without stable reference points, both geometric and celestial, timing drifts, festivals misalign, agricultural schedules fail. Irrigation systems, crucial to sustaining populations in arid lands, are particularly sensitive. Canals, basins, and terraces must follow precise gradients. A misalignment of even a few centimeters over hundreds of meters can cause flooding, stagnation, or failed crops. Without reliable baselines, the infrastructure of sustenance falters, and with it, the foundations of power. In this context, the Great Pyramid takes on a new significance. It is not simply a tomb. It is not simply a monument to a king. It is a calibration object, a central standard against which the physical and societal order could be measured and enforced. Its geometric discipline is, in essence, a statement of authority. The state, the central administration, and the pharaoh claim the right to stabilize the world, to anchor both labor and law, to enforce a fixed frame upon reality itself. Constraint discipline becomes political stability. The fidelity of corners, slopes, and axes is inseparable from the fidelity of administration. By ensuring that every stone obeyed its rule, the builders created a visible manifestation of centralized power. Obedience to geometry mirrored obedience to governance. If the pyramid could not drift, then neither could the society's systems, at least in principle. It was an assertion that order, both physical and social, was achievable, measurable, and enforceable. And herein lies the philosophical core. Civilization is, in many ways, an exercise in measurement. Every social, architectural, and economic system depends upon invariance, consistent units, reliable time, predictable flows of labor and resources. When baselines are stable, complexity can flourish, cities rise, canals run true, labor is coordinated, calendars synchronize, knowledge accumulates, systems scale beyond the limits of individual perception because the collective relies on stable reference points. Conversely, when baselines collapse, the consequences ripple outward. Governance falters, buildings deform, irrigation misaligns, calendars drift, errors compound. The fragility of uncalibrated systems becomes evident. Without disciplined measurement, society cannot scale, cannot endure, and cannot reproduce its achievements reliably. Stability depends on constancy, order depends on fidelity, civilization depends on constraint. The Great Pyramid, in this light, is a masterstroke of civilization itself. Its unbroken geometry over decades embodies the principle that measurement enables scale. Its preserved corners and slope encode the knowledge that order is not abstract but practical. The pyramid enforces constancy in the same way that law enforces behavior or architecture enforces space. It is a fixed point not just for stone, but for society. And yet, the shadow of fragility remains. Later, pyramids demonstrate what happens when oversight diminishes, when the culture of constraint weakens. Slopes begin to vary, corners drift, alignment relaxes, structures endure, but with subtle compromise. The lesson is unmistakable. Precision must be preserved at both technical and societal levels, or the network of dependencies begins to unravel. So the philosophical question emerges with urgency. If civilizations scale only when their measurements stabilize, what happens when the baselines collapse? When centralized authority fails, when standardization erodes, when calibration is ignored? The pyramid itself hints at the consequences. Later constructions, despite their grandeur, never achieved the same absolute fidelity. Systems drift, errors compound. The culture of measurement weakens, and with it the power that depends on it. The Great Pyramid is a warning as much as it is a marvel. It demonstrates that mastery of constraint, of angles, slopes, orientation, ratios, is inseparable from mastery of society. Its geometric discipline is inseparable from administrative discipline. Its enduring stability is a reminder that civilization cannot thrive on improvisation alone. It thrives only when the constants are respected, when baselines are fixed, when fidelity to process is enforced across generations. And as we step back from the desert and observe the unbroken lines, the flawless corners, the unwavering slope, we are forced to confront the ultimate question that the monument embodies. When the baselines collapse, what remains standing? Look around the modern world, and the contrast is stark. We inhabit a civilization of extraordinary technological capacity. We have machines that lift heavier than ever before, cranes that move tons with precision unimaginable to ancient eyes, and computers that calculate, model, and simulate entire structures before the first stone is set. We have materials stronger than granite, alloys that resist corrosion, and engineering knowledge codified in vast manuals and standards. And yet, despite all this, fragility persists. Bridges fail. High-rise buildings sway, projects explode in cost, in time, in expectation. Entire systems, carefully planned on paper, collapse under unforeseen pressures, human error, or drift in reference points we assume to be absolute. We know the statistics. Mega projects routinely exceed budgets by tens of %. Timelines stretch far beyond original planning. Reference frames, the conceptual and operational coordinates that allow multiple teams to work in concert, drift. Margins are miscalculated, alignments shift. Even with high-tech tools, the chain of fidelity from plan to execution is fragile, vulnerable to organizational, human, and logistical drift. It is a paradox. The more we know, the more complex we allow our systems to become, and the more sensitive they are to breakdown. Contrast this with the Great Pyramid. The ancient builders lacked computers, steel, or mechanized cranes. They could not model their plans on screens. They did not have standardized international codes. They did not rely on large-scale automation or mass-produced components. Yet somehow, across 20 to 27 years of construction, across thousands of workers rotating in and out, across the shifting sands of the Giza Plateau, one thing never drifted. The slope did not change. The corners held. The orientation remained constant. Every layer, every hidden chamber, every corridor maintained fidelity to a system of constraints. And here lies the paradox. The technology we assume to be indispensable, machines, tools, material strength, was not the critical factor for enduring precision. The lost technology, the true marvel, was procedural. It was the capacity to enforce invariant standards across time and space, to hold a chosen slope as sacred, to insist that corners obey right angles with almost absurd fidelity, to maintain orientation toward the stars, the horizon, and cardinal directions with unwavering discipline. This is the principle the Great Pyramid demonstrates. Procedural fidelity can outlast tools, machinery, and even civilizations themselves. Modern projects often fail, not because our machines are weak, but because our procedures are incomplete, unanchored, or poorly enforced. A deviation of mere millimeters in a bridge's reference lines can cascade into structural stress, misalignment, and eventual failure. Budgets balloon not merely from inefficiency, but because drift in planning, oversight, and coordination accumulates over time. Systems that assume stability but lack it are inherently fragile. The ancient builders, in contrast, understood the consequence of drift. They did not rely solely on tools or manpower, they relied on method. Every measurement, every alignment, every placement was embedded in a culture of verification and correction. The Great Pyramid is instructive here. Consider the corner angles, accurate to tens of arc seconds, maintained across a base of over 230 meters. Consider the slope ratios maintained across all faces and through the interior. Consider the internal chambers, aligned with cardinal axes, resistant to drift despite the pressures of massive stone overhead. This was not a miracle of material, it was a miracle of method. The procedure itself enforces fidelity. It is procedural intelligence encoded in stone. And yet, we struggle to replicate such precision today, even with superior tools. The lesson is not about lifting heavier stones, but about maintaining the integrity of the system over time. Modern projects collapse under the weight of their own complexity because the constraint network, the invisible web of checks, balances, and standardized references, is incomplete or inconsistent. In contrast, the ancient builders encoded the constraint network directly into the architecture. The stone itself becomes a monitor, a reminder, a standard. The pyramid enforces its own fidelity. This invites reflection on scale. We often assume that technological advancement alone is sufficient to manage complex systems. The ancient builders remind us otherwise. Complexity is manageable only when the network of constraints is rigorous, verified, and culturally enforced. One can have the strongest materials, the largest budgets, and the most brilliant calculations, but without procedural fidelity, the system drifts and the cascade of error becomes inevitable. The Great Pyramid also illuminates an existential dimension of engineering. Its discipline was human, cultural, and procedural, not solely material. It depended on shared understanding, on continuity of knowledge, on rigorous adherence to process across decades and generations. Modern projects, despite technological abundance, are often fractured socially. Teams change, knowledge is siloed, oversight weakens, communication falters. The drift of human systems mirrors the drift of physical systems. Precision is not merely a property of stone or steel, it is a property of coordinated action maintained across time. And here the philosophical layer emerges. Perhaps the lost technology of the ancients was not found in tools, but in societal calibration. They understood that stability is achieved not by brute force, but by embedding constancy into the procedure itself, by enforcing invariant baselines against which every action, measurement, and placement is compared. They encoded resilience directly into the workflow, the hierarchy, and the culture of construction. The pyramid stands today precisely because it is a procedural artifact as much as a structural one. Its endurance is a testament to the integration of method and labor, oversight and knowledge, intention and action. When systems lose constraint, when the chain of verification weakens, when oversight falters, when fidelity is sacrificed for expedience, fragility emerges. Bridges sway, buildings crack, budgets spiral, and schedules collapse. Drift, once tolerated, becomes amplified. Complexity outpaces control. Yet the Great Pyramid demonstrates that when constraint is respected, even the most massive structures, constructed without computers or steel, can endure for millennia. The secret is not in the tools, it is in the discipline, the cultural commitment to procedural constancy. Modern engineers, confronted with mega-project failures, often search for solutions in better materials, smarter algorithms, or bigger cranes. The ancient lesson is subtler. The solution lies in the invisible skeleton of constraint, a network of rules enforced across time, personnel, and scale. The pyramid does not fail because it has no steel. It succeeds because it embeds the principle that everything is measured, corrected, and maintained against a fixed reference. It teaches that procedural rigor, cultural enforcement, and disciplined oversight are as important as the materials themselves. And the implications extend beyond construction. Any complex system, infrastructure, finance, governance, or even societal organization requires reference frames, verification networks, and cultural fidelity to succeed. When these drift, no matter how advanced the tools, the system is vulnerable. The Great Pyramid becomes a mirror. It reflects the consequences of constraint and the consequences of its absence. Perhaps the ultimate lesson is haunting in its simplicity. Human systems, regardless of their sophistication, endure only insofar as their baselines are stabilized. Machines, software, and materials cannot substitute for procedural discipline. Constraint, fidelity, and enforcement across time are the true technologies of durability. And when those systems fail, when the baseline drifts and the network unravels, the consequences ripple outward, visible in every collapse, every budget overrun, every misaligned project of our own age. What remains when systems lose constraint? Across the sun-bleached plateau of Giza, the wind whispers over 2.3 million stones. Each massive block, some weighing more than 15 tons, is in place, immutable, yet there is one feature more remarkable than their weight, their arrangement, or their sheer scale: the slope. It never breaks. Over decades of labor, under the oversight of thousands of hands, through the heat of the desert and the changes of rains, the chosen angle holds. It is the one constant, the invisible thread that binds the entire structure together. Not the height, not the interior chambers, not even the alignment to the stars, though all these are extraordinary in their own right. It is the rule itself that persists. That unwavering commitment to consistency is the true miracle of the Great Pyramid. We have spent centuries marveling at the lifting of stone, the ingenious ramps, the planning of manpower. But perhaps we have been asking the wrong question. The mystery is not how stone was moved. It is how a rule was preserved, how a civilization could maintain a geometric constraint across generations, across a workforce measured in the thousands, across the vast, shifting expanse of the Giza Plateau. Every other detail, material, method, monument, is subordinate to this principle. In this, the pyramid teaches us something profound about the nature of human achievement. Constraint is the backbone of stability. The builders understood that without adherence to a standard, chaos would seep into every layer. One misaligned course could ripple outward, skewing walls, deforming chambers, compromising alignment. The slope is not a decorative choice. It is a calibration, a reference, a principle that enforces consistency across the entire project. And so, for the builders, fidelity to rule became a discipline, a cultural requirement, a manifestation of authority. In that discipline, the pyramid finds its immortality. Consider the contrast with later pyramids, with modern projects, even with civilizations themselves. Where the rule is ignored or relaxed, structures warp, budgets swell, labor misaligns, trust falters. In the Great Pyramid, constraint is not incidental. It is codified in stone, encoded in labor, enforced through generations. It is the invisible scaffolding that supports both the architecture and the society that produced it. And it is precisely this discipline that elevates Khufu's pyramid above all others, not the stones themselves, not the raw ambition, but the procedural rigor that allowed the form to survive millennia. This principle extends beyond architecture. Civilization itself is built on baselines, units of measure, calendars, alignments, governance. They all depend on constancy. The Egyptians may not have conceptualized process control in the language of modern engineering, but they understood its effect. A deviation in measurement is not merely technical, it is political, social, economic. A misaligned canal or field boundary undermines irrigation, taxation, food distribution. An error in alignment or slope compromises architecture, labor schedules, and ceremonial timing. To stabilize the physical is to stabilize the human. Constraint is not limitation, it is empowerment. And yet, the lesson is haunting. Look around the modern world. Our societies are vast, our technologies powerful, our reach unprecedented, and still we struggle with drift. Mega projects collapse under their own complexity. Budgets balloon, reference frames shift. We have steel, concrete, computers, satellites, and still we fail to maintain the invisible lines of consistency that allow scale and stability. The ancients lacked all of these tools, and yet they preserved what we so often lose: invariance. Perhaps the lost technology of their time was not material, but procedural. The discipline to enforce a rule, the culture to uphold it, the systems to verify it, the authority to make it inviolate. The Great Pyramid in this sense is not merely a building, it is a mirror, reflecting the relationship between human systems and the principles that govern them. Civilizations rise not solely by invention, by machinery, by the raw manipulation of materials. They rise by adherence to principle, by the rigorous maintenance of baselines, by the faithfulness of method. Where constraint is enforced, achievement endures. Where constraint collapses, fragility follows. The stones of Giza teach us that permanence is as much cultural as it is physical. And now, as we consider our own age, the question becomes personal, societal, existential. If our own reference frames weaken, if we abandon fidelity to the measures, standards, and baselines that organize knowledge, technology, and governance, what in our world will never be violated? Which principles, which truths, which structures will hold when our systems drift, when oversight falters, when human error accumulates? And when that which we assumed immutable finally bends, what will be lost and what will endure? The Great Pyramid endures because it obeys a rule that is larger than ambition, larger than labor, larger than individual authority. Its slope is a promise that constancy can outlast human lives, generations, even entire empires. But the lesson is double-edged. The inviolable rule is not guaranteed by material, but by discipline. In any civilization, past or present, the moment constraint weakens, the moment baselines collapse, fragility emerges. The pyramid whispers this truth across millennia. Permanence is earned, not inherited. And so, in the quiet of the desert, we confront the final paradox. The Great Pyramid is both achievement and warning. It asks us to consider what we are anchoring in our own world. What are the rules we choose to preserve, and how rigorously do we enforce them? What baselines are we stabilizing so that the systems we build, the societies we inhabit, and the knowledge we accumulate do not drift into chaos? It is not a question of stone, it is a question of civilization. In the end, the apex, the slope, the angles, the orientation, they are more than geometry. They are the embodiment of a principle. Across millions of stones, through decades of labor, through generations, the rule never breaks. And perhaps the deepest question the Great Pyramid leaves for us is this: if our own reference frames weaken, if the disciplines that sustain our knowledge, our society, and our understanding falter, then what in our world will never be violated? And what happens when it is? The desert stretches endlessly beyond the pyramid, the wind shifting sands across an unforgiving landscape. Yet the Great Pyramid stands, a monument to fidelity, a calibration in stone, a testament to the enduring power of constraint. It endures because the rule was inviolable, and the question it leaves us with, this final, haunting, existential question, lingers long after the last stone, long after the last measured line, long after the desert wind has passed. When the baselines fail, what remains? And when they do, will we be prepared to understand what that means? Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.